All right, thanks. I'll just dive right in. Let me know if you have trouble hearing me, just wave your hand in the back there. I'm not sure how far this will carry, and there's no portable mic. All right, so I'll try to get to the very last slide as quickly as possible because the bulk of this presentation is intended to motivate the discussion which will hopefully come right after it. I've been working on Windows networking about 11 years, and the past 6 of those years have been spent on rewriting the networking stack, which will ship in Windows Vista. So I'll be talking a little bit about the out-of-box changes in behavior for basically every Windows desktop that runs Vista. I'll also talk a little bit about some of the capabilities that are there under the covers but that are not turned on by default. Along the way, I'll talk about some of the lessons we've learned about the approaches we took to making these huge changes and where I think we need to go from here based on those lessons. So first, a quick look at the timeline. So I started to work on the design in '99. By 2001, we had our first milestone. Mid-2002, we had TCP data exchanges up and running. Late 2003, we had the new stack in the main builds for Windows, meaning that every install of the pre-release OS had the new stack up and running. So a couple things to point out here. First of all, work on the new stack was ongoing at the same time we were working on Windows 2000, XP, Server 2003, XPSP2. It's part of why it took so long. But then secondly, also that we've been sort of fine-tuning the behavior of the stack for the past 3 years. So a lot of what you'll see already reflects what we've learned from the deployments that we've had, both internally as well as across the beta programs that we've had. Those lessons are continuing up until this very moment. In fact, I had to change the slide deck just now because we had changes that affect what I'm going to say today as recently as this past week. These are some of the guys who've been working on the new networking stack. You can imagine this grew from a team of about a couple people doing the work to the picture you see in front of you right now. So what's new? I mentioned earlier that V6 is on by default. That means that Windows Desktop will discover V6 connectivity. If it's behind a NAT, it'll configure a Teredo address for itself if it can. If it detects a 6-to-4 router, it'll pick up a 6-to-4 address and so on and so forth up through native V6 connectivity. There are a bunch of other changes as well. A few of them I'll talk about today, so I won't go into detail on them on this slide. We have built-in support for equal cost multipath routing, meaning that if a Windows machine sees equal cost routes to the same prefix, it'll actually multiplex its traffic over them. Black hole router detection, which has been historically a big one for us from the point of view of support costs, is enabled by default. We've changed the set of options that we negotiate by default with TCP. Window scaling is always negotiated by default, as our selective acknowledgements. And then we've upgraded the algorithms that we use for congestion control and loss recovery. So we're now a new Reno stack. FRTO support is enabled by default, as well as DSAC. Our old ephemeral port assignment used to assign ports from 1024 all the way up to 5,000. That's changed. So now it's compliant with the IANA specs in that area, meaning it starts from about 49K and goes up to 64K. And then finally, across the board, there's been a fairly pervasive focus on getting rid of registry keys. So I kind of laughed earlier when someone said maybe folks would just go turn off IPv6 in the registry because that's not the way it's done. So as much as possible, we try to figure out what the right thing is to do dynamically and tune the stack's behavior on the fly. So that's it for the stuff that is turned on right out of the box. In addition, there's quite a lot that we put in that we left disabled either because we didn't have a compelling customer case for it or because it had infrastructure implications and the infrastructure wasn't quite there yet, or for any number of other reasons. One is that ECN is configurable. It was actually on by default in some of the earlier betas, and just based on the issues that we've seen with various equipment from vendors not working or kind of choking when it sees ECN bits, we've scaled that back a little bit. It's a strong host model, meaning by default we'll only send out an interface, we'll only use source addresses on the interface to which they're assigned. You can actually configure the weak host mode as well in environments where that's important. I'll skip over a few of these because I'm trying really hard to get to that last slide in the amount of time I have. Per socket, we have extended statistics support. That means essentially that you can turn on TCP eStats, the eStats MIB, on any given connection and look in detail at what's going on from the point of view of the congestion algorithm, flow control, and so forth. Connection offload is built in if you have the hardware that supports it. And then we support attempting IPsec on all traffic, so you can put the machine into a mode where whenever it's communicating with a peer, it will always try to negotiate IPsec. And if it succeeds, it'll proceed in secure mode. Otherwise, it'll fall back to clear text mode. And then I'll skip through the last few of these. So the first case study, looking at what we actually went through in getting to the point where we felt comfortable in turning on IPv6 by default. You can think of this as happening in multiple phases. The first phase was where we were doing our experimental bootstrapping. We had an add-on for Windows 2000 that you could download and install that added IPv6 capabilities. And we used that to do early self-hosting, improved it in XPSP2 Windows Server 2003. And right now, you know, we have, well, not public 6-4, but public Teredo services. So by default, out of the box, any machine that's behind a NAT can configure a Teredo address for itself. In the second phase, which overlapped quite a bit with this first phase, we identified and tackled a lot of issues that had to do with the infrastructure and the services, actually making it so that you could use V6 in a real way. So native IPv6 and ISOTAP routers, getting equipment up to spec, finding the bugs and getting them fixed so that we could at least do our internal deployments. So our IT departments could support users who are running IPv4 and IPv6 in dual stack mode. Things have gotten a lot better. There's still a little bit of work to do, particularly when you start looking at some of the higher end applications in a lot of the equipment. But currently, customers actually can start to look at doing IPv6 deployments, at least on a limited scale, using the technology that's currently available. Phase 3 is widespread deployment, and by that I mean getting to the point where we can turn it on by default for everyone, which is the case, which has been the case since Windows Vista Beta 2. And secondly, actually being able to run in an IPv6 only mode. So we have a growing number of desktops on our corporate network that basically only get IPv6 connectivity, and we do this so that we can identify what are the things that have built-in dependencies on IPv4, so we can find those dependencies and fix them before our customers find them. What have we learned? The hard problems, you have to find those early, and the only way to find them is to get code out there up and running. I'm curious, just by a show of hands, how many folks here have V6 hosts on their networks? Okay, yeah, I was thinking it would be a higher number. But the key lesson here is that if you don't have a V6 host on your network, you should start looking into, I mean, you will have them soon if you're an operator, because as soon as Windows Vista ships, you'll start seeing this V6 traffic on your networks. The second lesson, figure out what the right questions are. And what I mean by that is figure out what are the questions that you really need to answer in order to be able to make a simple yes-no decision on deployment. In our case, we had to look at a wide range of things. What are the key applications that users expect to work, both on the desktop as well as on the server, in order to have a realistic story for supporting an IPv6 deployment? And that applies both in the consumer operating system, folks, running their PCs at home, as well as in the corporate environment. And the answers are very different. So it's important to figure out what the environments are you want to support and start getting your hands dirty and getting things out there up and running, qualifying equipment, and so on. This is an ongoing effort for us. We still find issues with equipment, and environments that have issues with IPv6, but we're at the point now where we're comfortable with the current configuration of Windows Vista and RC1 and RC2, and V6 is enabled by default. The bulk of hosts will get V6 connectivity via Teredo, which means that if they're behind a NAT, we'll actually tunnel IPv6 inside UDP. Now, Teredo is a special case because it never actually registers addresses in the DNS, and simply having a Teredo address will not cause you to use Quad A records from the DNS. I'll talk about that a little bit as part of this next discussion. So the key thing to take away from that is currently the primary use that you'll see for IPv6 is in peer-to-peer applications. Applications that have their own mechanisms for exchanging IP addresses, IPv4 as well as IPv6 addresses. So, V6 capable nodes will ask for both A and Quad A records. And there was a presentation, I believe, at NANOG, several NANOGs ago maybe, about the impact that this would have on the DNS infrastructure. What we actually have seen internally is that there's been minimal impact on our DNS infrastructure. We haven't seen any significant data on public deployments, in other words, the behavior of Vista, Beta 1, Beta 2 machines in the wild. Dan Kaminsky, who's sort of an expert on DNS, had some research that he did that I've put up there. You can go look at his website on his take on the issue. But how do things currently work in RC1 of Vista? Well, first of all, this discussion only arises when you actually have a global IPv6 address. By default, the DNS clients in Vista will not query Quad A records unless there is a global IPv6 address. The way that the client works in RC1, some fine-tuning in RC2, is that it will send A queries first as part of devolution, and then when it gets back an authoritative answer, then it'll follow up with a Quad A query to that specific server. In general, what we expect is that this will result in a significantly smaller than 2x increase in the amount of load that you'll see for the DNS from V6 deployments. This is a change from Beta 2, and so far what we've seen is that this algorithm works fairly well for mixed mode deployments where you have both V4 and V6 records in the DNS. Now, what does this actually mean in practice? On the public network, an application will typically only have a global V6 address when or rather a node will only have a V6 address when some application is using IPv6. Teredo has this logic in place where it tries to configure an address, it tries to activate its Teredo IPv6 address just in time, basically when an application explicitly tries to use Teredo. Now, an additional change we made, which was even more conservative, is that if the only global address you have is a Teredo address, we won't send any Quad A queries at all. So this really scopes down the use of IPv6 in the default mode in networks where there is no native V6 or 6-to-4 deployment to purely peer-to-peer applications. So that includes some applications out of the box like our Windows collaboration feature, which uses peer name resolution to discover hosts dynamically and set up IPv6 connections between them. There's quite a bit more detail on this at the link that I put here on the presentation. So what do we learn from this? Well, the key lesson is that the feedback that we got third-hand via NANOG would have been great to get first-hand, actually. I'll have a place where you can send feedback at the end of this slide, but I'll go on to the next case study before I elaborate on that point. TCP receive window auto-tuning. So what does this do? The challenge we set for ourselves as part of overhauling this networking stack is to make this compelling. In other words, to take away, the old stack and replace it with the new one. We really want to be able to make a significant stride forward in the behavior of the networking stack, something that customers would actually care about, something that would resonate with them. One of the areas where we made such a big step is in the area of end-to-end TCP performance. Historically, the stack has been, and this is the case for many stacks, has been bounded by 64K window, which is the size of receive window that the TCP can advertise by default. Window scaling allows you to advertise a larger window, but window scaling isn't always enabled by default. Not all peers that you request window scaling from will honor it. Some equipment out there actually still gets confused when it sees the window scaling option. But we set out to tackle actually all of those issues and be able to scale the performance of the stack end to end across a variety of paths by default out of the box without any registry tweaking. So what was our design? Well, basically it was to estimate the bandwidth in the network on the receiver side, not on the sender side, which is a little bit more tricky, and to tune our window advertisement based on the estimates that we generate on an ongoing basis for any given connection. Now, for these estimates to be of any use to us, we have to enable window scaling, because without window scaling, the largest window we could advertise would be 64K anyway, so we'd never be able to keep the pipe full if keeping the pipe full meant having more than 64 kilobytes of data in flight between the two endpoints. So without really trying, our MSCOM, MSIT folks running a connection between a pair of, actually between a Vista box and a Win2K3 box, saw a 40x out-of-box improvement with this algorithm. And this is, when you think about it, when I talk about this algorithm, I usually have a picture which shows the discrepancies between the pipes over which a typical stack has to run over. You have everything from, a 64 kbps ISDN link with, tens of milliseconds of latency to a satellite link, with 100 megabits, capacity. And when you do the multipliers to find the bandwidth delay products, and you compare whatever bandwidth delay product you get to 64K, there actually is a big difference. In some cases, the difference is 40x. So now the immediate feedback that our MSIT folks had is, well, you're going to use up all the capacity in our network, and we need to be able to prioritize traffic. We also have support for policy-based QoS out of the box in Windows Vista, which allows end hosts to actually categorize the kind of traffic they have based on DSCP markings. And we're continuing to improve in that area. Now, so some of the responses are that we have group policy knobs in place so that you can roll out policies to an entire enterprise that will scale back the auto-tuning algorithms. Basically, it will artificially throttle itself and not keep the pipe as full as it could. And then the policy-based QoS I mentioned. Our expectation is that we'll start seeing paths get used a lot more efficiently. By default, by its nature, the algorithm is designed to sense what the available capacity is and try to use as much of it as it can without impacting any other TCP flows. That's what we've seen so far in practice. And the deployments that we've had have largely, the feedback from our beta testers has largely been ecstatic. We've also had feedback from service providers who have said, yeah, we've seen a spike, but the people who are actually getting the benefit are pretty happy with the throughput that they're getting. The expectation naturally is that if everyone on a network has an auto-tuning stack, what you would get is that everyone would get about the same share of bandwidth, which is what the goal is for TCP flow control in general. So the challenge here, as in the previous cases, how do we actually close the feedback loop? How do we monitor the behavior of an improvement like this on an ongoing basis, so that we understand better how to design the end host's behavior based on the requirements and observations that occur within the network infrastructure. That's a feedback loop that I think doesn't really exist today, and starting to get something like that going is one of the key subjects of this talk. Compound TCP is an algorithm where there's a real opportunity to do something in this area. I talked about auto-tuning, which is enabled by default and which will be enabled by default in Windows Vista in the client, which is shipping pretty soon. Compound TCP is an algorithm which is latent in the client, but we're looking to enable it by default in the server operating system, where it's much more compelling. The basic idea behind Compound TCP is to look at what it takes to recover from fairness on wide area networks, particularly wide area networks that are very high capacity, and ramp up into the available capacity faster than classic TCP does. Most of you are probably familiar with the sawtooth pattern that classic TCP has, and you're familiar with the degradation in pipe utilization that occurs over time as you repeatedly take a loss, and as the window gets larger and larger, it takes longer and longer to ramp back up to whatever throughput you had before. Vegas-style algorithms solve this by basing the windows that they use not on detection of loss, but on detection of variations in the latency, under the assumption that increasing latency is a sign that the pipe is starting to get oversubscribed. The question for us is whether we could take some of that approach, which historically has been very unfair to classic TCP flows, and incorporate it into the operating stack in a way which is not only fair, but also preserves a significant amount of the benefit. So what we ended up with is something we call Compound TCP. The algorithm is based on some work that Microsoft Research Asia did. It combines both a delay-based window with a loss-based window. The idea is that when your window is smaller, or when there's less buffering in the network, the loss-based component of the window dominates, so we behave more like a regular TCP. And as your window gets larger, or as the delay variations become more detectable, we start behaving more like a delay-based TCP, meaning we allow you to refill capacity faster. So results, the same MSCOM folks who saw the 40x improvement, when they turned on this algorithm, it gave them an additional 50% improvement, so about another doubling in throughput, which again is not that surprising when you look at the actual sawtooth graphs and you look at the amount of time that TCP spends in ramping up into high bandwidth, high capacity pipes. So we also have done some engagements with the UK MOD and the Stanford Linear Accelerator Center to understand the behavior of this algorithm, understand its fairness to other TCPs. So we have further confirmation that it recovers faster, and we also have evidence that it's actually more fair than high-speed TCP and a number of other algorithms. This is an area where we're continuing to do research. And so if there are folks here who are interested in this sort of problem, we're very, very interested in working with you and thinking through how we go about deploying logic like this on a scale that allows us to really understand it enough to roll it out, on a widespread basis. So I made it to my second to last slide, which is the key one. I've hinted at a lot of what this talk is really about. It's not really just about the changes that we made in Windows Vista. When you look at the timeline that we went through to actually get to the point we are at today with a completely new networking stack in Windows, about to ship to millions of people, and what that means for the internet. A lot of the work that we did was to actually establish a platform that would allow us to innovate a lot faster and would allow us to pull in a lot more new functionality on an ongoing basis into the networking stack. Being able to do that requires having a feedback loop between the folks who are deploying the end host software and the folks who are actually operating the networks in the wild, where that software manifests, all of the corner cases and all of the interesting behaviors that are key to establishing the viability of any particular algorithm, whether it's for congestion control or for flow control. Some of the things that we're looking at for future as future innovations on top of the platform that we have today is IPsec everywhere. So I mentioned that we'll actually try to use negotiate. We have a mode where we will try to negotiate IPsec between any pair of hosts, but that's not enabled by default. It's a latent capability, so you can go configure it. But it would be, what we'd really like is for to actually always attempt IPsec by default. What does that mean? What does it look like in deployment? What needs to be in the network to actually support such an operating mode? Peer-to-peer traffic patterns. I mentioned that Teredo is primarily leveraged by peer-to-peer applications, and because it's a platform capability that we're starting to use a lot more aggressively, you'll start seeing more and more applications relying on the peer-to-peer platform that's deployed that's available inside Windows Vista. That'll drive further changes in traffic patterns because it'll become a lot easier for even casual application writers to write applications that leverage peer-to-peer traffic patterns. And then finally, botnets, distributed denial of service, an ongoing area for us. We're always looking for ways we can make it harder to use the networking stack as a platform for launching distributed denial of service attacks. As much as possible, we'd like the cost to be pushed back onto the attackers wherever possible. So we've made changes in the past in that area. For instance, limiting the rate at which a Windows machine will make outgoing connections that are in the half-open state. And we're always looking for areas for improvements that we can make over that algorithm to make it even harder to launch denial of service attacks. So, with all that said, what do I actually propose? So this is the hard part, because engagements in general are tricky to design in a way that provides value for both ends of the engagement and also are sustainable on an ongoing basis. You don't want something too decoupled because then it just sort of atrophies, and you don't want something that's too high cost because then participating is high cost, so there's no real benefit. So what I'm sort of proposing and what we've come up with so far from our end is the notion of having open questions for now related to Windows Vista if there are concerns or areas where you'd like to know more about what we're doing or where you have feedback to offer us. And actually on a more regular basis have our engineers coming and answering questions, as well as you folks engaging with us and on the issues that you're facing and how they impact end nodes and how they impact the networking software that we're building. Part of that means actually starting to collect metrics around the behavior of both what the infrastructure sees as well as what the end hosts see. We've had very limited engagements with operators in the past for instance, in the case of auto-tuning. But I have a feeling that it might be something that kind of engagement might be something that's interesting to other folks. So we're open to that as well. And then just in general, keeping tabs on where we're making progress, where there are issues, and having a forum that folks just know about and can count on for bringing these sorts of concerns. And that's all I had. So I'm open to thoughts, questions, requests for clarifications. If you have feedback on anything you've heard from me, that's an alias you can send it to, TCP/IP feedback, and I'll take questions.
I have a question over here.
Where?
The other side.
Oh, sure.
Over here. I'm kind of curious about the performance improvement. Is that a Windows to Windows client to server interaction? Do you get the type of performance connecting to non-Microsoft servers?
For the auto-tuning, the only change that you'll just have to be running a Vista receiver. Any server that understands Windows scaling will give you, that improvement. And then for compound TCP, you just have to have it on the sender. because it's a sender side change. So in general, we don't really, I mean, obviously if you have a sender with compound TCP and a receiver with auto-tuning, then you'll get more of an improvement than if either side just has one of the algorithms. Does that answer your question?
It does, thanks. And I guess just the other general observation is TCP is one of those foundation things that you generally don't imagine really getting modified all that much without great review across a broad spectrum of folks. I mean, everything depends pretty much on the TCP stuff. So I'm wondering, is Vista going to be released with this new thing prior to that broad discussion-based interaction?
So just to be clear, the auto-tuning algorithm actually is standard TCP. It doesn't make any changes to the TCP protocol. All it's doing is it's changing the way that the receiver picks which window it advertises, which is well within the scope of the RFCs. Now the part that actually does change behavior is compound TCP. And compound TCP is not enabled by default in Vista, and that's part of the reason why it's not enabled by default. It's because we want to start engaging to understand its behavior better. Question?
Yes, sir. Noticed keenly that there's going to be, or planned to be support, I'm not sure if you had said it was working or not, for more or perhaps easier access to diffserv configs, perhaps a socket option when established. Can you hear me?
Could you repeat the question?
I'm not quite done yet. You were saying, I heard there was planned support, apparently for easier access for user applications to set diffserv bits to define things upon binding to a socket.
Actually, there's easier support for administrators to configure diffserv bits for applications.
Sure. I guess that my
so basically you can roll out a policy saying, the following application, XE, gets the following marking, on its traffic, or traffic that matches the following pattern, on a organizational wide, gets the following marking.
I see. So that's not supposed to be something that is a replacement perhaps for queuing control upstream, or is it supposed to be able to push that congestion closer to the client? Perhaps saying to a set of machines that you're all behind a DSL and you only have a half meg up. My router can't sort, so I'd like all the machines to do so and pretend as if the congestion is occurring perhaps within the IP stack itself. Is that happening? Something like that?
Well, specifically this is for cases where you have an admin in the picture, someone who has actual control over the machines. And can configure them. So it's not for consumer environments. For instance, a service provider offering service to folks at home. Does that answer your question?
Yep. Thank you.
All right.
So, John Christoph, I have 3 questions. If it's going to take you more than a minute to answer, I'll be happy to take it offline. The first is you'd mentioned something about how if you get an authoritative answer back, you'll then send the quad A query, and I just wanted you to maybe clarify that because usually you're probably hitting a recursive server, and so the answer is not actually authoritative per se. The second question was regarding the choice of ephemeral ports that you use, and I know the Unixes have tended to use the range that you mentioned, but why not just use the entire 1024 and everything above just as default? And then lastly, can you say anything about SCTP in your implementation and maybe sort of what things you see that are going to be, who's using that, what they're going to use it for, that sort of thing?
Okay. First question, I'm not quite sure I got it, but basically if we get it back an answer, a specific answer, then we'll follow up with a quad A query to that specific server. Okay. Does that make sense?
Yeah, you had said authoritative answer, and I just wanted to clarify that.
Okay, and then the second question was about
ephemeral ports. The ephemeral ports.
Oh yeah, ephemeral ports. So now the issue with that is that there are actually a lot of registered ports that we need to avoid. This has been a problem in the past. In the 1024 to 49K, well, 1024 to 5000 certainly, there are ports that are registered to people with IANA, which would originally conflict with the dynamic assignment logic.
But
So-
these are, I was assuming maybe incorrectly, these are just ports you're choosing as a source port for an application, or are you talking about
Yeah,
something
source
else?
ports. So for instance, if your ephemeral port assignment allows you to choose ports in the range 1024 to 5,000, what it means is that an application may get a source port which later someone else will come along and try and bind to because it's registered to them. Does that make sense?
Okay.
And then they
I
fail
think-
and they're unhappy.
Okay. And then the last one was SCTP.
Oh yeah, SCTP. So we've looked at SCTP over the years. Currently, we don't have any plans to support it. Some of the key features that SCTP could potentially offer, we've tried to incorporate support for instance, better support for multi-homing on connections. We have APIs that make it a little easier for applications to do that. The biggest stopper for us has been the willingness and the investment in getting people moved over to a completely new transport protocol, and what that means for them. So in some ways, it's like, for us, it's like tackling another IPv6, at the same time that we're tackling the IPv6.
We're 5 minutes, actually more than 5 minutes behind schedule, so let's just finish up these questions we have out there, and then we'll move on.
You had mentioned that your diff-serve control point stuff is intended for an environment with an administrator. Anything to prevent it or discourage it, or from being used by rogue applications in such environments, or or rogue users administering their boxes to do bad things with it?
Well, if users have admin privileges on their machines, then nothing can prevent them from abusing any packet marking scheme. So the answer is no. We haven't done anything significant there. Yeah.
I have a question on Teredo and IPv6. So my understanding is that Teredo will not be turned on if IPv6 native is available. So it's more maybe a comment. So coming from somebody who is trying to deploy this to some customers, what happened when we have a native v6 connection to one customer, another customer has a v4 and NAT and use Teredo? My understanding also is that today there is no such thing as a Teredo relay to connect Teredo clients to native IPv6 clients. So what should happen?
Okay, quick clarification. So why is it that you say Teredo won't be used if you have, Teredo won't be preferred over a native IPv6 address, if that's what you're saying. But you can have both the native and the 64 and the Teredo address all at the same time.
So essentially my question is, what happened when two customers want to do a peer-to-peer application based on IPv6? One of them has native IPv6, and the other one has only IPv4 NAT and then Teredo.
So that leads me to my second question, which is that, or rather my second comment, which is that currently there's no, there aren't widely deployed Teredo relays, but there's nothing to prevent people from deploying Teredo relays. So in the environments where we currently use Teredo aggressively, we have some other mechanism other than DNS to exchange addresses. So the peer name resolution protocol is an example. And the out-of-box applications that leverage Teredo, they use PNRP to exchange addresses. And in general, that's sort of the model. If you have native IPv6 connectivity and you need to talk to someone that only has Teredo, then either there has to be someone who's willing to relay traffic for you, or...
So another way to ask my question
I'm sorry, I need to cut this off. We are 10 minutes behind schedule, and we have to get in another
I'll be out
talk,
there
so.
during the break, I guess,
Yeah,
if you
I
have
invite you
more
to talk
questions.
at the lobby afterwards. So thank you very much.
Thanks.